In this lecture, I will discuss the forces that affect rotation of rigid bodies in the context of rotational dynamics. Thus far, we have discussed two types of motion. Motion along a linear trajectory, and also rotational motion about a fixed axis of rotation. However, in general, in nature, motion is a combination of those two types of motions together. We have both translational motion and rotational motion. Simple examples of that type of combination would be a football that is thrown in the air. So it is a projectile, but at the same time it also spins about an axis of rotation. A baseball that's thrown in the air, a basketball, even a bullet, which we've discussed as a projectile only, actually spins about a central axis. So it's a subject of those two types of motion. We also discussed kinematics of rotational motion, where I talked about quantities that are used to describe rotational motion. But now, in the context of dynamics, it's important to understand how forces affect rotation. So we know that in translational motion, when force is applied, an object accelerates. Then one can ask a question of what causes the angular acceleration of rotating object to change, to increase or decrease. What's responsible, the quantity that is responsible for the change in angular acceleration is called torque. In very general terms, torque is the tendency of an object to rotate when a force is applied with respect to a preselected axis of rotation. So for example, we have a door. Here are the hinges. Here is the doorknob. So if a force F is applied as shown, that is going to cause the door to rotate about an axis of rotation that passes through the hinges. The door will also rotate about the same axis if the force F is applied as in the second drawing. However, the amount of rotation that will be generated in the second example is different than the amount of rotation generated in the first example. Furthermore, if the force F is applied in this way, as the third picture shows, then the amount of rotation of the door will be different compared to the first and the second examples. So the force F is applied here at different positions with respect to that fixed axis of rotation. As a result, this door will rotate, but the rotation will be different because of where the force was applied, and also in the third case, how the force was applied. In the first two examples, we have the exact same force applied at different distance from the axis of rotation. So that is going to generate different amount of torque. In the third example, the force is applied at the same point or the same distance from the axis of rotation as in the first example. However, this force is angled with respect to the axis of rotation at an angle that is smaller than 90 degrees. Therefore, as a result, this force will generate different amount of torque compared to the force applied here. So then we can define the torque, tau, as the product of the force F and the lever arm L. Let's see what those components are in the above three drawings. So this is the door that I discussed on the previous slide. The axis of rotation is on the left-hand side, and then the force F is applied on the right-hand side of the door. The line on which the force F lies, this dotted line here, is called line of action of the force. The distance from the axis of rotation to the force, or to the line of action of the force, the distance at 90 degrees from the force or the line of action of the force is called the lever arm. In the next drawing, we have the force F applied at a certain angle to the door. So the line of action is here. The force F acts along this line of action. The perpendicular distance from the axis of rotation to the line of action of the force is the lever arm L. So this is extremely important to understand. The lever arm is always measured from the axis of rotation to the line of action of the force, and it's always perpendicular to that line. So in the first drawing, naturally, because the force is applied at 90 degrees to the door, the lever arm is just the distance from the axis of rotation to the line of action of the force. In the second drawing, since the force is applied at an angle to the door, the lever arm is the perpendicular distance from the axis of rotation to the line of action of the force. And here in the third drawing, the force is lined up along the axis that passes, along the line that passes through the axis of rotation. Therefore, there is no perpendicular distance from the axis of rotation to the line of action of the force, which means that the lever arm is 0. Therefore, in this example, this force is not going to cause the door to rotate. There will be no torque. And you can experiment by pushing on a door at your house with a force directed the way it's shown here, and you will find out that the door is not going to move. And it doesn't matter how much force you're going to apply, as long as it's applied the way it shows here, the door will not move. So one more time, the torque tau is equal to the product of the applied force L and the length of the lever arm L. Now, since the force is a vector quantity, that means that the torque is a vector quantity, and therefore there is direction associated with the torque. And so torque is positive when the force tends to produce a counterclockwise rotation about the fixed axis. And torque is negative when the force tends to produce a clockwise rotation about the fixed axis. The units for torque are the units of force multiplied by the units of length, so Newton meters. Notice that those are the same units that the work done by a force has. However, the units for work we select to be called joules. And here for torque we use Newton meters. So there should be no confusion what quantity is being discussed when you see the units. Here is an example of the application of the definition of torque. The Achilles tendon exerts a force of magnitude of 790 newtons. Determine the torque, magnitude and direction of this force about the ankle joint. So here is the ankle joint, that's the Achilles tendon, and point P here is the point where the force on the heel is applied by the Achilles tendon. So the force F is applied at the point P. The rotation happens about the ankle joint. So force F is applied or acts along a line that is not perpendicular to the distance between the axis of rotation and point P. So therefore the lever arm is the perpendicular distance shown here from the axis of rotation to the line of action of the force. And we know that this angle here is 55 degrees, and the distance between point P and the axis of rotation is 3.6 times 10 to the negative 2 meters. So let's see how the torque is calculated. The torque is calculated as the product of the force and the lever arm. So the lever arm is going to be equal to 3.6 times 10 to the negative 2 times cosine of 55 degrees. Substituting that in the expression for the torque and substituting the value for the force F gives us a torque of 15 Newton meters. Let's discuss the effect of the net force acting on a rigid body as far as the equilibrium of the body is concerned. We say that the rigid body is in equilibrium when neither its linear motion nor its rotational motion changes, which simply means that its linear acceleration, both x and y components, are zero, which means that the net force in x direction and the net force in y direction is zero, and its angular acceleration is zero. So the net torque that's acting on this rigid body is zero as well. So we have a general condition for equilibrium which states that the net force on an object is zero, the net torque on an object is zero, and then this object is in equilibrium. There is no rotation, there is no acceleration during rotation, there is no acceleration during translation. So a rigid body is in equilibrium if it has zero translational acceleration and zero angular acceleration. In equilibrium, the sum of the externally applied forces is zero, and the sum of the externally applied torques is zero. Using these three conditions could help us solve various problems involving the equilibrium of objects. The reasoning strategy for solving those types of problems is to select an object to which the equations of equilibrium are to be applied. Then draw a free body diagram that shows all of the external forces acting on the object. Then choose a convenient set of x and y axes and resolve all forces into components that lie along those axes. Apply the equations that specify the balance of force at equilibrium. Set the net force in the x and y directions equal to zero. Then select the convenient axis of rotation, set the sum of all torques about this axis equal to zero, solve the equations for the desired unknown quantities. So here is one example of equilibrium that I will use to sort of show the procedure of how to deal with those types of problems. A woman whose weight is 530 newtons is poised at the right end of a diving board with length 3.9 meters. The board has negligible weight and is supported by a fulcrum 1.4 meters away from the left end. Find the forces that the bolt and the fulcrum exert on the board. So here is the diving board, here is the woman. So her weight pushes down on the board, which in turn pushes down on the fulcrum, and so the fulcrum will react with a normal force pointing up. At the same time, the board is also pushing up on the bolt, and so therefore the bolt is going to apply reaction force down towards the base. So here is the free body diagram of the board. This is the weight of the woman pointing straight down. The reaction on the fulcrum, on the board from the fulcrum, F2 points up, and then F1 is the reaction of the bolt to the board pushing up. So the reaction of the bolt is pointing straight down. Okay, so I'm going to choose my x and y axis as shown in this square, and I'm going to choose the axis of rotation to be at the bolt. So I'm going to measure all lever arms lengths from this axis of rotation. Okay, so we know that the fulcrum is 1.4 meters from the bolt, so therefore the lever arm for F2 is 1.4 meters. And then we also know that the length of the board is 3.9 meters, so this is the lever arm for the weight of the woman. So about this selected axis of rotation, I'm going to write all torques that are not zero add them together and set the sum to 0. Why is the sum equal to 0? Because this board is in equilibrium right now. There is no motion up or down. The torque of force F1 right here is 0 because that force passes through, the line of action of that force essentially passes through the axis of rotation. So the lever arm for this force is 0, no torque. The torque of the force F2 is equal to F2 times L2, where L2 is the lever arm for that force. And remember the definition of positive and negative torque. So F2 tends to rotate the board in counterclockwise direction, so therefore the torque that it will produce is positive. And so this quantity here enters with a positive sign. For the weight of the woman, the torque that the weight produces is in clockwise direction, so therefore it will be negative. And so that's why we get the minus here. So we get minus W times LW, where LW, again, is the lever arm for the weight of the woman. And so the sum of all torques, the net torque is 0, because, again, this board doesn't move. It's in equilibrium. And from here I saw for the force F2, substitute the values that I know, and it turns out that force F2 is equal to 1,480 newtons. So I know the weight of the woman. I found force F2. What's left to find is force F1. I will find the force from the equation for the net force in y direction. So in y direction we have minus F1. The minus sign appears because this force points in a direction opposite to what the positive direction is, plus F2 minus W, and we set this net force equal to 0. So substituting the values for F2 and W in this equation gives me that the force is equal to, the force F1 is equal to 950 newtons. So this is a typical example of the use of the conditions for equilibrium of net force equal to 0 and net torque equal to 0 to solve problems about equilibrium of objects. I discussed the center of mass concept in the chapter about impulse and momentum and how to define or calculate the position of the center of mass. So now if you look at the center of mass of an object, you can consider that all of the mass of the object essentially is focused at that point. And therefore, under the action of Earth's gravity, that's where the weight of the object will be focused as well. And so this point, in terms of calculating weight, is known as center of gravity. So the center of gravity of a rigid body is the point at which its weight can be considered to act when the torque due to the weight is being calculated. And so in this example here, this is a board that is attached at its right end. You can think of that as a door as well. So the axis of rotation is at this hinge. The center of mass is right midway between the two ends. So that is also where the weight of this board is focused, and so therefore the torque of the weight is considered with respect to that point. So the torque arm is just half of the length of this board. This only is true, meaning the position of the center of gravity right in between the two ends, when an object is uniform in how the mass is distributed inside this object. If the mass is distributed in a way that is not uniform, for example, imagine a baseball bat, then the center of gravity will be shifted towards the heavier end. For our purposes, in general, we are going to consider nice symmetric objects for which the center of gravity will be focused at the geometric center of the object. So then how do you calculate the position of the center of gravity of an object? So here is my board with an axis of rotation attached to the right end. It has a center of gravity at this position, x1, measured from the axis of rotation. And I also have a mass with weight W2 placed a position x2 or distance x2 from the axis of rotation. So now I have two different gravitational forces acting in this system. So where exactly is the center of gravity of the system? The center of gravity of this system is calculated simply by taking the product of weight and lever arm, basically the torque of W1, add to that the torque of W2, and divide this by the sum of the weights of those two objects, the board and this mass that's placed on the board. That means that if I put a fulcrum here at the position of the calculated center of gravity, or the calculated position of the center of gravity, the board with this mass on top of it will be balanced. There will be no rotation, no translation, so this system will be in equilibrium. So in a sense, there can be made another statement for the definition of the center of gravity position, and that would be for a system of objects, the center of gravity is the point where if you put the fulcrum in that point, the system is in equilibrium and there is no rotation or translation. So here's an example of how we calculate the center of gravity of a more complex object. This example is about the center of gravity of an arm. The horizontal arm in this drawing here is composed of three parts. The upper arm, right here, which has a weight W1 of 17 newtons. The lower arm, right here, which has a weight W2 of 11 newtons. And the hand itself, which has a weight of W3 of 4.2 newtons. The axis of rotation for the arm is the shoulder joint. So the distances for each of the three weights are 0.13 meters for the upper arm. The distances to the center of gravity for each of those three parts of the arm are 0.13 meters for the upper arm, 0.38 meters for the lower arm, 0.61 meters for the hand. So what is the position of the center of gravity of the arm relative to the shoulder joint? The definition of the center of gravity position was the torque of each weight added together divided by the total weight of the object. So for the upper arm we have 17 newtons times 0.13 meters. For the lower arm we have 11 newtons times 0.38 meters. For the hand we have 4.2 newtons times 0.61 meters divided by the total of the weight, and that gives us 0.28 meters for the position of the center of gravity of the entire arm with respect to the shoulder joint. So that will be located somewhere right here. Now let's discuss the situation where there is no equilibrium. There is angular acceleration. So we talked about Newton's second law in terms of dynamics of linear motion of an object. Now let's talk about Newton's second law in terms of rotation of a rigid body. So I start with Newton's second law for translational motion. The force is equal to mass times translational acceleration. So I know that there is a relationship between applied force and torque. And so therefore, and this relationship is that the torque is equal to the force times the lever arm. And then on the other hand, I know that the tangential acceleration is equal to, for a rotating object, is equal to the angular acceleration times the distance from the axis of rotation. So in my case here, I'm looking at this airplane, model airplane, which is held by a string to rotate about this circular trajectory. So the tangential force Ft is shown in this drawing, and the distance from the axis of rotation is the radius of this circle. So then the torque is simply the tangential force times the radius of rotation, and the tangential acceleration is the radius of rotation times the angular acceleration. Substituting those into the original second Newton law statement gives me the following result. The torque that acts on this model airplane is equal to the product of mass times radius of the circular trajectory squared times the angular acceleration. Now, this product of mass and radius to the second power, or distance from the axis of rotation to the second power, is called moment of inertia. So this derivation that I showed here with this example of the model airplane is applicable for point particle types of objects. So small objects like this model airplane, or a small ball, or something like that. How does this derivation change when I have in mind an actual rigid body with finite size that cannot be approximated with a point particle? So here is my rigid body. It's just a randomly shaped slab of material that rotates about a fixed axis that passes right through here. And so this rigid body is made of multiple particles with different masses and located at different distance from the axis of rotation. So when this rigid body rotates, all of these particles are under the action of forces. So we have external forces and then we have internal forces. The internal forces are shown in this drawing right here. And these internal forces are essentially action-reaction pairs. They are equal in magnitude, opposite in direction, and by Newton's third law, they cancel each other out. They do not contribute to the net force acting on the slab. So for each individual particle here, I can calculate the torque using the definition that I showed on the previous slide. So for the first particle, the torque is equal to the product of the mass of that particle and the distance of that particle to the axis of rotation squared times the angular acceleration of the particle. For the second particle, I can write its own expression for the torque, for the third particle, and so on and so forth. For all n particles that make up this rigid body, I have an expression for the torque written in terms of the mass of each particle and the distance to the axis of rotation to the second power of this particle times the angular acceleration of the particle. Remember that this rigid body rotates is 1, meaning all the positions of the particles are fixed. They do not move within the body as it rotates. So therefore, all of these particles will have to cover the same angle for the same amount of time during the rotation. Therefore, they all have the same angular acceleration. So if I sum all of these terms, what I get is the net torque will be equal to the sum of all moments of inertia, which we just called the moment of inertia of the rigid body, times the angular acceleration of this rigid body. Notice that the moment of inertia of this rigid body depends on the product of the mass and the distance to the axis of rotation to the second power, and it is a sum of individual terms that correspond to these particles. So each term has different value because each particle has a different mass and each particle is a different distance from the axis of rotation. So that means that the moment of inertia here is a function of the mass distribution inside this rigid body. Meaning you can have several different rigid bodies with the exact same mass, but the mass is distributed differently with respect to the axis of rotation, And when you calculate their moment of inertia, you are going to get different values. So even though the masses are the same, just due to the fact how the mass is distributed around the axis of rotation, you will get different values for the moment of inertia. And so the rotational analog of Newton's second law for rigid body rotating about a fixed axis states that the net external torque right here is equal to the moment of inertia right here times the angular acceleration right here. And the moment of inertia is equal to the sum of the moment of inertia of all individual particles that make up this rigid body. For this definition here to work, the angular acceleration must be expressed in radians per second squared. So let's show an example calculation of the moment of inertia and how it changes depending on the mass distribution about the selected axis of rotation. Two particles, each have mass m, are fixed at the end of a thin rod. The length of the rod is L. Find the moment of inertia when this object rotates relative to an axis that is perpendicular to the rod at one end and at the center. So here is the rod, those are the two particles. The axis of rotation passes through one end of the rod in the first configuration, and then in the second configuration we have the two masses at the ends of the rod, and the axis of rotation passes through the center of the rod. From the definition of moment of inertia, which is the sum of mass times distance to the axis of rotation squared, we get for the first particle m1 times r1 squared plus m2 times r2 squared gives us m times 0 to the second power. The distance from particle m1 to the axis of rotation is 0, plus m times l to the second power. The distance from m2 to the axis of rotation is the length of the rod, which was L. And so the result of the calculation gives us that the moment of inertia of this system is equal to ml squared. So if you know the mass of these particles and the length of the rod, you can calculate the value of the moment of inertia with respect to this axis of rotation. Now let's see how the moment of inertia changes when we move the axis of rotation to pass through the middle of the rod. In this case, from the definition of moment of inertia, we have the mass of the first particle times the distance to the axis of rotation, which is L divided by 2 to the second power, plus the mass of the other particle times the distance to the axis of rotation, which is L divided by 2 to the second power. And when you calculate this sum, you get that the moment of inertia is 1/2 ml squared. So this moment of inertia is 1/2 of the previous moment of inertia. So here we have R is equal to ml squared. And here we have R is equal to ml squared divided by 2. So this is a very good illustration of how the mass distribution with respect to the axis of rotation changes the value of the moment of inertia for essentially the same configuration of the system. And so the moments of inertia, the formulas for various types of symmetric objects have been calculated, and in this table they are provided to be used when solving problems. So we have the moment of inertia of a thin-walled hollow cylinder or a hoop, a solid disc or cylinder, a rod with length L for an axis of rotation that passes through the center or through the middle, rod of length L for an axis of rotation that passes through one end, solid sphere for an axis of rotation passing through the center, solid sphere for an axis that is tangent to the sphere, hollow sphere or spherical shell, and then we have a rectangular sheet. And so these are the common ones. So this table can be used for problems where the rigid body that is rotating is composed of shapes that are symmetric like so. For example, a dumbbell will be a solid sphere, two solid spheres with a connected with a rod, or you can have something else. The point is that you can break down your more complex shape into simple shapes like that, calculate the individual moments of inertia, add the results together, and that gives you the total moment of inertia. The units for moment of inertia are the units of mass times the units of distance to the second power, so that would be kilograms times meters squared. So let's look at this problem and use the concept of moment of inertia to solve it. The combined moment of inertia of the dual pulley is 50 kilograms meter squared. The crate right here weighs 4,420 newtons. A tension of 2,150 newtons is maintained in the cable attached to the motor. Find the angular acceleration of the dual pulley. So here is the dual pulley, here is the crate attached to this cable, and then the dual pulley is connected to the motor right here. So let's look at the free body diagrams for the pulley and the crate. So for the pulley, we have tension in the cable that is attached, that is connecting the pulley to the motor. So this tension will create torque with lever arm equal to the radius of the large part of the large pulley. Then we have the weight of the pulley pushing down on the axle. We have the tension due to the crate hanging on the cable on the other side, straight down. And the force P here is the reaction force due to all the forces that act in the system. And then for the crate, we have the weight of the crate pulling down, and then there's tension T2 prime directed up along the cable, should be equal to that tension right here. So in y direction, we have the net force is equal to T2 prime minus mg is equal to may. So this is for the crate. And for the pulley, we have that the net torque is equal to the torque of tension 1 times the torque arm, or lever arm, minus tension 2 times its lever arm, and that should be equal to the moment of inertia times the acceleration. So I can express the tension T2 prime, which is equal to T2, from the net force in y direction equation. And I get this result, T2 is equal to mg plus may. And I can substitute in the torque equation. And also, I will replace the acceleration ay with, because that is the tangential acceleration for point on the pulley here, with its angular acceleration relationship. So ay is equal to L2 times alpha, where L2 is the torque arm from the axis of rotation of the pulley to where this cable is attached. And so when I combine the whole thing, it gives me that T1 times L1 is equal to T1 times L1 minus mg plus may times L2 is equal to I alpha. So this is the final expression in terms of the known tension T1, the known lever arms, the known angular acceleration, the known mass, and the known moment of inertia. So from here I can solve for the angular acceleration alpha. After rearranging the terms here, the expression that I get is that alpha is equal to T1 L1 minus mg L2. That's divided by I plus mL2 squared. So I know everything on the right side. So when I substitute the values, it gives me that the angular acceleration is equal to 6.3 radians per second squared. So for those types of problems, I always start with the net force, the second Newton law for the net force. and then express the net force accordingly depending on what the problem gives me. Then I also add the rotational form of the second law, which is the net torque is equal to moment of inertia times angular acceleration. And I then write explicitly the net torque in terms of the forces provided. And then I combine the two with appropriate substitutions to get an expression for my the quantity. And so in this case, that was the angular acceleration. We saw in the sections about translational motion that when force is applied, an object moves a certain distance or displaces a certain distance, work is done by that force. So let's see what is the equivalent of work in rotational motion and also the energy that an object possesses when it rotates. So here is a drawing of a car wheel that rotates, and or a pulley that rotates, and the rotation is caused by pulling with a force F on a rope that is running around the pulley. So this pulley has a radius r, and let's say the angle of rotation is theta. And during that rotation, this much of an arc is going to be traveled by a point on the edge from here to here. So the work done by this force F will be simply equal to the product of the force and the length of arc, so F times S. However, we know that this arc is equal to the length of the arc is equal to the radius of this pulley times the angle of rotation. So if I substitute here, that gives me that the work done is equal to F times R times theta. And now, accounting for the fact that F times R is equal to the torque of that force F, I finally get the definition of work in rotation. And that is that the work done by this force is equal to the torque of the force times the angular displacement. So the rotational work is equal to the torque due to that force F times the angle of rotation or the angular displacement. The rotational work done by a constant torque in turning an object through an angle is WR for rotation is equal to tau times theta. The requirement here is that the angle must be expressed in radians. As before, the units for work are joules. Now let's look at the kinetic energy formula for rotational motion. So let's start with the kinetic energy of translation. So you have a rotating object like this disk, grab a point or a particle at the edge. It has tangential velocity vt, so it has a kinetic energy which is calculated with 1/2 mvt squared. But there is a relationship between the angular velocity of rotation of this point and its linear velocity, and this relationship is given by this formula here. So if I substitute in the kinetic energy expression, that gives me 1/2 mr squared omega squared. Then I can do the same procedure for all particles in the rigid body and add the results together. And then after regrouping as shown here, I get that the kinetic energy of rotation specifically is equal to 1/2 times the moment of inertia times the angular velocity to the second power. So the rotational kinetic energy of a rigid rotating object is Ke sub r for rotation is equal to 1/2 times the moment of inertia times the angular velocity to the second power. The requirement here again is that the angular velocity must be expressed in radians per second. The units for kinetic energy, in this case for rotational kinetic energy, will be joules as well. If an object undergoes rotational and translational motion at the same time, like so, then the kinetic energy term that can be assigned to that object, let's call it kinetic energy total, will be equal to the sum of the kinetic energy of translation plus the kinetic energy of rotation, or that will be 1/2 mvt squared plus 1/2 I omega squared. Here I also would like to point out that when you're calculating the rotational kinetic energy term, this moment of inertia value you would get from the table that I discussed a few slides ago, from this table. So typically problems involve hoops or hollow cylinders, discs or cylinders, spheres, solid spheres or spherical shells that are rolling, and so in those cases the moment of inertia in the calculation will be calculated using the corresponding formula depending on the shape. So we have one more thing to discuss. We need to find the analog of linear momentum for rotational motion. The analog for linear momentum is the angular momentum. The angular momentum, L, of a body rotating about a fixed axis is the product of the body's moment of inertia and its angular velocity with respect to that axis. So the angular momentum L is the product of the moment of inertia with respect to an axis of rotation and the angular velocity with respect to that axis. Again, the requirement here is that the angular velocity is in radians per second. The units for angular momentum are kilogram meters squared per second. Just like for linear momentum, there was a principle of conservation of linear momentum. The same way, there is a principle of conservation of the angular momentum. The simplest example that can illustrate that principle would be a figure skater that's, rotates in place. So when the figure skater rotates in place, but her arms are stretched out like so, she would be rotating with smaller angular speed because her moment of inertia is big. But when she brings her arms close, she is going to rotate much faster because her moment of inertia now is smaller. But her angular momentum remains the same because there's barely any friction with the ice. So when her arms are stretched, her moment of inertia is big, therefore her angular velocity is small, and the angular momentum value is a certain amount. When she brings her hands in, her moment of inertia goes down, her angular velocity goes up, and the product gives us the same angular momentum as before. And so if I were to write the expression for the angular momentum in each situation, here we have I1 omega 1, here we have I2 omega 2, and then the conservation of angular momentum requires that the two are equal to each other, and that's how we write it. So let's apply a conservation of angular momentum to this problem about a satellite in an elliptical orbit. And this also applies for the Earth orbiting around the Sun as well. So an artificial satellite is placed in an elliptical orbit about the Earth. Its point of closest approach is 8.37 times 10 to the 6th meters. That is called perigee, right here, perigee. And then the point of greatest distance is 25.1 times 10 to the 6 meters from the center of the Earth, so that is apogee right here. The speed of the satellite at the perigee is 8,450 meters per second. So the speed right here, VP, is 8,450 meters per second. Find the speed at apogee. So VA is what we're looking for. So this is a problem about conservation of angular momentum. So when the satellite is closer to the center of the Earth, it's going to go faster around the orbit here, as opposed to when the satellite is further away from the center of the Earth. The only forces that act in the system are the gravitational forces between the satellite and the Earth, and that's a pair of action-reaction forces, and according to Newton's third law, they do not produce a net force. So therefore, the angular momentum of rotation of this satellite here, the product of moment of inertia and angular velocity, will be constant. It doesn't change anywhere around the orbit. So that means that the angular momentum at the apogee must be equal to the angular momentum at the perigee. So the angular momentum for a point particle, because the satellite is essentially a point particle with respect to the size of the Earth and the size of the orbit, is simply mr squared. And the angular velocity can be written in terms of the linear velocity as v divided by r. So substituting both in the expressions for the angular momentum at the 2 points, I get the following relationship. The mass of the satellite times the radius of at apogee to the second power times the speed at apogee divided by the radius at apogee is equal to the mass of the satellite times the radius at perigee to the second power divided by the speed at perigee divided by the radius at perigee. So after simplifying the expression, the result is that the distance at apogee times the speed at apogee is equal to the distance at perigee times the speed at perigee. Solving for VA gives me, and substituting the values that I know, gives me that the speed at apogee is equal to 2,820 meters per second. So this concludes the lecture on rotational dynamics. As you saw, there is a, like in the previous lecture on rotational kinematics, there is a lot of similarity between the two types of motions. The laws essentially apply very similarly, with the one exception being the moment of inertia, which plays similar role to mass. However, the moment of inertia depends on the choice of axis of rotation and how the mass of the rigid body is distributed around this axis of rotation. But otherwise, we have linear momentum, angular momentum, we have force, torque, we have angular acceleration, linear acceleration, we have rotational kinetic energy, translational kinetic energy. So there are a lot of analogy between the two types of motions in terms of the way the motions are described and explained.